Okay, let's get going. Yeah, welcome back, everyone. So what I want to do today, so I'm going to finish up the kind of the proof I was in the middle of doing. So I can start on this backboard and you don't have to move the camera. So really what I was trying to do, I was working in this expansion of the real field. Does not define Z. And I wanted to take, I mean, the full result is that you would work, take an E in R to the N, and you say this is E sigma, and you would want to show that then these two dimensions that we were discussing, let's write it here, dimension in the usual naive sense, so that is the maximum n such that the projection, or sorry, maximum m such that the projection on R to the M picks up interior, that this is equal to the, what we call the upper Minkowski dimension. As I said before, I will do this here for n equals 2, and I will really just give the proof for closed. And I think there's one small part where I'm going to cheat a little bit so to make the counting easier so that I don't have to talk about the sigma, but more or less the main argument, the full argument will be there. Okay, so then let me remind you of a couple of things that we introduced last time because they're really crucial. I want to draw the picture again. So maybe I do this here. So remember that if you take E is subset now in R2, then we introduce the following functions. I mean, so first of all, maybe I say this now, so I can get this out of the way. When I write E sub x, then this will always denote the fiber over x and over the first coordinate. So that would be the y in 0, 1 such that x comma y is in E. But sometimes, and this would be crucial, I will often have to denote the direction in the other, I mean, so this is to draw this right here. This would be everything above x, but sometimes I'll also have to denote everything above y in some sense. So that would be in the other direction. So if I write the index at the top, and really what I mean by this is will be this fiber, so going to the right. Okay, and then the functions that I defined last time was this f sub e, and so this really went from 0, 1 squared to 0, 1, and that picked for every x and y that would pick the minimum in this fiber over x, so in here, such that it lies above y. So intersection y to infinity, and then in order to be always defined, we add 2. Okay, so if again this kind of this, if you can see this, if E lives somewhere here, then this picks the minimum element in E over this line. If you fix the y and let the x just vary, and so in this case, this point here would be f of fe of xy. In this case, I drew it so that it looks continuous. Of course, we only know this kind of minimum functions are lower semi-continuous, so we only know that the points of discontinuity are nowhere dense for each of those y's. And what we showed last time was that the set of all these discontinuities. So when you let y vary, that this is a d sigma set. So last time, let me put this. So last time this set, maybe let me just write it out. So this the union of E with all these points of discontinuity is d sigma. So here this is, no, so the bracket's the wrong way around. It's d is a point of discontinuity of this function. So for each y, we have this function that you see up there, and we know that the set of discontinuities of, I mean, really, the parameter set of discontinuities is d sigma. So in particular, that means that if you know that each of those fibers, so each of those fibers is nowhere dense, so each of this one is nowhere dense, then you know that each of the fibers of this big set is also nowhere dense. I'll mention that again. I just want to state this kind of. Okay, and so now I'm ready to prove this theorem. And really what I'm going to do, now I move over here since it's, now what I'm going to do is I will first reduce to the case, and really the only interesting case will be, let me write this here, is where the dimension of E is 1. So when there's doesn't have interior, but you have one of the projection that picks up interior. That's really the case. Okay, so let me now spend the next 10 minutes or so getting rid of all the other cases. And at one point I do cheat a little bit, but it's hopefully not too bad. So really now what we have is 0, 1, 2 closed, and we want to show that this is the case. So now we get rid of the boring cases. So if E has interior, then, well, the dimension of E is equal to 2. But you can check this kind of an easy exercise in Minkowski dimension. If you have a set which has interior, then the upper Minkowski dimension is 2. Okay, so in the case that E is interior, this is easy. So now let's go to the other case. If the dimension of E is 0, so that means that in both directions, so it doesn't have interior, and in both directions it doesn't pick up interior. So then we know that both coordinate projections have empty interior. So then we know that then both P, it's on the first coordinate and on the second coordinate, are nowhere dense. And hence M now. You even get something stronger. Note also the union of those is M now. It's nowhere dense, then M is M. Okay.
Taking for granted that projections of the sigmas are the sigma. I guess that's.
Yeah, or if it's really in the case that it's compact, then the projection is compact too. But yes, I mean, even if this will be whole this sigma, then you take a projection of the. But even yes, even the more general case is actually also true. And then let me write this down here. Then the dimension of M is bounded by, well, the dimension of surely of this. Because the E is a subset of the Cartesian product of the projections. It's also a subset of the I'm not 100% sure, I think, whether this already is good enough, but it's surely good enough if you now take here the union of those two and take the Cartesian product. And now you know that both of these sets here have them in Kopf's dimension null, so their product also has dimension null. So it's also M null. And so now we have taken care of the cases that E has interior and E has dimension 0. So the only case we really have to take care now, as I pointed out, let me move this up now, is the case that the dimension of E is equal to 1. Okay. And so now I really have to, so now assume or reduce the case that the dimension E is equal to 1. So we have that, not sure actually whether I need this, but let's assume this. So assume that E1 of this has interior. Otherwise, change the coordinates. Okay, so now what I want to do is, so now I still could have the case that fibers, so in this picture, pick up a large chunk of the dimension. So that I do want to rule out. So now it's that set x to be in 0, 1, and suppose that for those x, the fiber, so if you look at the picture up there, the fiber up, that best picks up interior. So you can show, and this is at least as an exercise, I don't want to do this, I don't think I said this at the time, A is the sigma. Okay. So by the strong bare category theorem, A has either interior or is nowhere dense. Okay, and so in this case, if you're nowhere dense, and of course we know that you are null. Now by so now we know that E doesn't have interior. So we can rule out this case that this has interior, because we had this kind of result earlier on. I'm not precisely what the number that if you have the sigma set, and you know that the set of points where it has interior in the fiber is large, so has interior, then the whole thing would have interior. This was this kind of version of Kuratowski-Ulam that we stated. So that then means that since E does not have interior, A is M now. And so from that, okay. So I want to write this here. So if A is non-empty, then the Minkowski dimension of everything that lies in one of these fibers that picks up large interior, so all the x, comma y in E, such that x is in A, has dimension 1. Or if it's, okay, if you throw away the assumption of non-emptiness and you get smaller equal to 1, which is both fine. So in this case, you know, so the argument is, so you know that you have few fibers, and then over each fiber you can at most pick up 1. So that gives you, with a little bit of counting, that this is the. Okay. Good. So now now I will cheat a tiny bit, because I think I didn't end it up all the way correctly and only realized this morning. So so we know that the union it's one of the properties of many of these notions of dimensions. This should be M's here, of course, that the dimension of the union of two sets is the maximum of the dimension of the twos. We can essentially throw this set out. So where do you pick up interior? One has to be a little bit careful. So then now what I say is we deduce to the case that Ex has empty interior. Okay, so as you've seen me do it this kind of the last few weeks, I'm taking this kind of very technical proof, and I'm trying to get it to a point where it's really easy to follow without all these kind of everything counting. The point where I'm cheating here now, and I do want to point this out, and I will say to keep them more or less kind of all the notation that coming a little bit easier to handle, is that if you throw this out, you have to somehow show that you get a closed set, which you don't. You get a d sigma set, and I'm doing this for closed sets. But you can do this in a uniform way, or kind of even in the counting argument, I can tell you what you have to change. And then you find. So what you could do is I mean, you're not throwing out precisely this set, but take the closure, the set the same dimension, and then you're fine. But then you could get to a d sigma set or the closed set. And I'll tell you, I will now assume that we stay here in the closed case, and I will tell you how do you do this then for the d sigma sets. So similarly, reduce to the case so that the other fibers, so this is always, of course, for all x in 0, 1, so that the EYs have empty interior. For all y in 0, 1. Okay. So what I've now done, and this is really the case where I really do want to give you a proof, is the case that if you look at the picture up here, you have this set in E square, and I reduce the case that it doesn't have interior. One of the projection picks up interior, and all the fibers are 0 dimensional. Okay. And now let me write this kind of what I now assume and when I want to find a contradiction. So now what I assume is towards a contradiction. Suppose that the upper Minkowski dimension of E is not 1. So it's strictly larger than 1 for some. Let's call this D for dimension. Okay. So now what I'm going to show is I will show you that there's a contradiction. So I will show that then one of these fibers will have to pick up dimension. So I will show that these families here cannot be uniformly M now. Okay. All right. So let me now write down so what we have. So we have that this is positive. We know that we assume that EX and EX should be down here, have empty interior. So we know they are nowhere dense. And not only that, we had this kind of these are the sigma families for sure. And so if we had this theorem that says if they are nowhere dense, they're uniformly M null. So that means this families here, EX and EY, are uniformly M null. Okay. And so not only, so this is one thing we need. So we know that all these fibers in this picture over there, that they're uniformly M null. But what we also know is this kind of that, and this is why we worked so hard last time, is the point of discontinuity in each of these graphs, that is also M null. That's really what we use quite crucially. So by 6.7, I think is the set, as we said, okay, we said that the set, I have to give this a name. Let's call this, sorry, I call this whole thing, I think I called DE. Just have a name for that. The set DE is D sigma. And each of the, because we know that all the EX are nowhere dense, so the E, what do I need? The EYs I need, okay. And DEY is nowhere dense because EY is nowhere dense, and so this family, so hence the family of all of them is uniformly M null. Okay. So again, we know that each of the fibers are uniformly M null, and this set is M null. Just knowing that these two things are M null will not be enough. Really, I'll show you in a second why we need that these points of discontinuity are uniformly M null. So uniformly. Okay. Good. Okay, so this is the setup. I will now, here's what I want to delete. I think I'm going to keep this for a second. I will erase these. Okay, now what we really do have to do is do some box counting. And so I tried out the last 2 weeks to come up to change the argument so that we really don't have to do this kind of box counting in the way that I'm not presenting it, but I couldn't really make it work or at least I couldn't find, I mean, you can make it work, but I still couldn't find a way that was easier. So recall that when we talk about Minkowski dimension, I write this here, then really what we were doing was we were counting this number of boxes. So for a given radius, would kind of NER would be the minimum number of boxes of radius R that you needed to cover E. And so if this was somehow C times R to the minus D, then this was the Minkowski dimension. But in this kind of picture, you can choose whatever balls you like, right? There's no kind of boxes you like. So there's no, if you have a set something like this, then you can really take these kind of balls, right, to cover it. And so now what I need is a little bit more control over what kind of boxes you're allowed to take. But this will not change the Minkowski dimension. So they will give you an argument why it doesn't change the Minkowski dimension, why it doesn't change all these kind of things. I have to do it to make the argument not completely messy. So I want to introduce some more notation. It's a very simple notation. So for X subset R to the N, and I think I wanted to run this here with M instead of 2 to the M. So now essentially what I do, I want to restrict myself to boxes of radius coming 1 over M. And I want to have these boxes instead of having any kind of balls. I really want to make sure that I have these kind of boxes, right? I take these boxes and I take them, okay, I should have 5 here. And so instead of being allowed to take any boxes that cover these things, I will ask them to be these kind of boxes. Here it turns out a couple of more, but what you will see that in the limit, that doesn't matter whether you allow just these boxes coming from the grid or whether you're allowing this kind of balls in there. So here it's write this out. So what I now want to define is a slightly different counting thing. And so instead of having the number that covers any of those, what I want to take is the cardinality. I'll write this here so I have enough space. The cardinality of the set of all ij's such that they live in 0, 1 to m minus 1 squared, such that E intersects with the corresponding box. So what I mean by that is that if you take this interval here, okay, or this box, well, this is not in 0, 1. So let's multiply this by m to the minus 1. And then what they want to count those boxes that intersect with X. Okay, so instead of allowing any kind of boxes in this thing, I allow only those boxes that lie here in the grid. If you think about this, is an easy exercise that this does not matter. In the case, I mean, hopefully, again, I didn't convince myself of something too wrong, is that if you take this one here, so the minimum numbers of E that you can cover by boxes, let's say boxes really instead of balls, of radius m to the minus 1, then this is surely smaller or equal to this one here, because you restrict the number of the things of boxes you're allowed to take. You're allowed to take any boxes, and here you have to restrict yourself to the ones in the in this grid. But you can check that that is again bounded from below by this. And if you don't, I mean, really, I only going to use this for n equals 1 and n equals 2, and then n equals 1 and n equals 2 is okay. Maybe see you'll have a box in here, and so see if then this would be the optimal box, and I mean, instead we would have at most 4 times as many. That's really kind of the idea here. But this doesn't change in the limit. This would be just a constant factor here. So it wouldn't change the dimension at all. Okay, so and what we're going to do in this now I'm going to draw this picture is we're going to start counting these boxes in this sense. Okay. All right. Okay. Okay, so now I'm going to pick some things with this in. So now I'm going to pick M and N. So M and in the naturals and P and R larger than 0, such that the following is true. So remember that our assumption is that the dimension of E, the upper Minkowski dimension, it has least D, and this is larger than 1. And all these families, EX, EY, and D of EY, DE of are uniformly M now. So I now pick an M such that somehow witnesses that I need many boxes to cover E, but already I need few boxes to cover these things. So I pick, first of all, let this P be still smaller than 1 if you add it to 1. So then this is the assumption that the dimension of E is large. So this, you know that the dimension of E is larger than D. Okay, so if you look at these boxes, that will give you that eventually you will find an M such that you cover more than M to the D boxes plus some scalar. And so now the second thing, what I'm going to say is that we already know that for each X, comma Y in 0, 1, for these families already are small. So that would give you that the max of NMEX, MMEY, and now the same for the points of discontinuity, that this is smaller than M to the P. Okay, so now I'm ready to finally draw the picture. I have it. So this is supposed to be 0, 1 squared. Now I have to be really careful in drawing these boxes. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what do these equalities mean? So in particular, 2 means, so E now lives somewhere in here, and I will draw this in a moment. this tells you that the first thing is that E hits many boxes. Okay, so many of these boxes I will color in a second, but really the kind of properties 3 says that in each of these fibers there are very few things. And a priori, if you have no restriction on definability, you could easily find a set which has, I mean, very, very small fibers, but hits most of these things. So that's not, I mean, in general, this is really no problem to construct. So without this and without this kind of definability, you would truly find sets that satisfy this, but this here will be the crucial thing. So now what I'm going to do is I will try to draw a little bit here of E. So E might be some, maybe I should use the color. Maybe E is a line like this here, and then something like this. It doesn't matter that it's too precise, but you see the okay, maybe one right here. So now I could highlight all these boxes, right? I mean, I could highlight all these boxes where E lies in. I will highlight just a few of them to show you which one I really want to care about. Let's say. Mm-hmm. Okay. So what's the difference between these different boxes? So why did I highlight some of them and others I did not? So the point is what do these what do these points of discontinuity means? The points of discontinuity are those where you pick, let's for example take this line here, take this y, then the points of discontinuity of this function f of e something over y are those points where the kind of the minimum function has a point of discontinuity. So remember that, so this function here, then the next point here would of course not go down because the minimum has to be above. So it would here, this function for that would jump up here, right? So here would be a point of discontinuity. Similar, like for example, if you take your y up here, then the point of discontinuity would be here, here, or this one here. I should actually make yellow. And so the kind of the points I marked here, so I didn't, so the box I didn't color is where you have points of discontinuity. Look at this. This one should be fine too. And this one is not because you have a point of discontinuity here. There's a point of discontinuity here. So you see that in this picture, you get, I highlighted these kind of boxes, and what this kind of M null will give you here, what this kind of M null gives you here would be that few of these boxes are actually not highlighted. Okay. So the set of these yellow boxes in compared to the number of these yellow boxes and compared to all of the boxes that cover E will be very, very close. So most of these boxes will actually be boxes where you don't have a point of discontinuity. And if you don't have a point of discontinuity, then what you're going to see is that in this box for everything, and I will draw this in a second again when I write it down, is that the fibers will have to be large because these functions are too continuous. They are continuous. Okay, so I will now make the whole argument, and this is really just now an easy counting plus one application of the intermediate value theorem. Okay. So let me define things here. So define two sets. F will be all the ij's in 0, 1 to the m minus 1 squared, such that the corresponding boxes intersect that they intersect with E. So this F, if you go back to the picture, if you look at the picture, will be all those boxes that intersect with these wiggly lines. Then I call G. G will be the set of all the yellow boxes, so the boxes that I shared. So these are all the boxes in F such that there are no points of discontinuity of the corresponding wiggly lines. So that means that in the interval I plus j, now I plus to I plus 1 cross j, so j is really kind of the fiber we pick, intersect the points of discontinuity is empty. Okay, so this really means we're not looking at all these different kind of fibers we could pick, but really just the ones that coming from the grid. And so now what I'm going to show, is that the cardinality of these two things is more or less the same. Okay. I do want to move this up here in a second. So what I want to need is, first of all, that I want to use that this, I call it Fj, is this function E that picks up for this j over m, so for this endpoint here, the minimum above that line. So let me move this up. Keep this here. And so the Fj, so for example, if this one here is on this j over m, then with this graph here, this is Fe over j over m. So this would be the graph of this Fj. This line here. So this line, if this is your point j over m, then this line would be this kind of the graph and would go until here, and then it would jump, would jump here and continue like this. All right. Okay. Okay, so now we're really down. Now we start finally. We start counting. Okay. So by 3, well, I wanted, as I said, I want to say that the cardinality of F and G is almost the same. So I will take F and I'll throw out G, and I will claim that the cardinality of that is small. Okay. So okay. So what we can do, we can definitely bound. So if you look at the number of boxes, we can simply take all boxes in so remember, if you have the set like this, and we simply take in this direction all boxes of size that will be at most m. But we know that the points of discontinuity for each of these lines here, for each of these boxes, is small. So by 3, it's bounded by m to the p. So this is, we know that for each of these lines, this is smaller than m to the p. And so this is smaller than m plus 1 plus p. So in particular, it's smaller than 3 to the md. So that means thus by 1 and 2, we get that the size of G is rather large. So cardinality of G, the cardinality of G is at least 2m to the d. And because we throw it out as most m to the d many. Okay. Right. And so now, okay, I will take a subset, or I will take a further subset, and this will be the following. So let's I will define the set, and I will say what is the point of this. So set H to be the ij's in F. So this will be another set we're going to throw out from G, and those are the sets where the box or the interval is kept in the box. So minus 1 j plus 1. Okay. I have to have an example. I should have. Let me draw another wiggly line here. So this would be yeah, okay, well here, this works out. So for example, if you take this j here, so this j, this is j, and this is this is ij, then you see over this thing here, this line is continuous, but and we have a point in here, but this is not contained in this interval. So it moves out here. And we know because it's continuous, and this will be the crucial thing, you know that this has to hit a line. So we'll have these kind of things where it's continuous, but if it is continuous and it leaves the box in some sense, then it will always hit one of these fibers. And here, this here is an example. So here, over this one here, this line here is continuous, but you leave the interval, so you have to hit one of this. And because we know that these fibers here are small, that cannot happen all that much. Okay, so where do I want to? Maybe I keep this. Erase this. Okay, so now we'll consider precisely this case. So I will consider the case, take one of these ij's and suppose this is in G, but not in H. So the minimum function above this line coming from J is continuous, but it leaves the box. Then, so just to sum this up again, one, we know, as I said, Fj is continuous on this box. And there is something in this box. And there is something x0. Such that this is in the box. J plus 1, yes. But, and so this is all from being in G, but from not being in H, there has to be also be something outside the box. So there is x1 also in this box, but whose image is outside of the box. Such that f of j x1 is not in the box. Okay. So it's that, yes. So note that, of course, I mean, you see this here, all these wiggly lines. These wiggly lines, if you have something like this, the function value is always above it, right? So you cannot, these kind of lines cannot leave this box downstairs. They can only leave the box upstairs. So this really has to be, so this has to be larger or larger than m minus 1 j plus 1, because you have, if you leave the box, you have to leave it upstairs. Okay, and so then by obviously now by the intermediate value theorem, if you have something above this point and some below this point and the function is continuous, you have to have someone who hits this line. So thus by intermediate value theorem, there is, let's say, x2 in this such that f the minimum over x2 is equal to mj plus 1. Okay. And thus, okay, thus this box, the box I, comma, I plus 1, intersects the fiber coming from j plus 1. It's not empty. So this means, let's say this way, for every I and j in G, which we know there are many of, that's the whole point, we get that then if for every j, so for every I, and if you know that j is in this large set, then there also has to be, I has to be in that fiber. So there are many of those, and now that means that there has to be many of those. And we know, and that's why we get where they get the contradiction, is that this is a fiber, and we know that the fibers are all small. So we get from this here, this is a point where we get from the largeness of the whole set to the largeness of the fiber. And then now I make this precise, and the counting is now really easy. So let me, what do I want to keep? Maybe I keep this arm. This. Okay. So thus by 3, the cardinality of G set minus H is bounded by the following. You can take whatever J you like, so there are at most M of them, but for each of them, you know that the cardinality of all the J's, or all the I's for which this can be true, is bounded by the cardinality of that fiber, and there are few. So then the kind of, this is smaller than the cardinality of wait, of the fiber I have to uniformly MP. This was, I mean, really because this is the cardinality of this fiber. M to the minus 1 j plus 1. And so this is smaller than I plus 1. And this is smaller than m to the d. So by 1, the cardinality of this H has to be large. So by 1, or maybe actually not 1 anymore, it's this one here, star. By star, the cardinality of H is larger or equal to the cardinality of G minus the cardinality of the complement. And so that's greater or equal to m to the d. Okay. Good. So now now what we have shown is that the set of boxes where you're continuous and where you do not leave the that these wiggly lines do not leave the box is large. So that means that if you look up there, all the yellow lines are of this form. There are many of them. Okay, so now we have that there are many of them. And now the last thing I have to do is to show that there is a large fiber. This now follows almost immediately. Yes, that's so H is it's not 100% precise because I would have to make sure that kind of the fiber, there are always few things in the fibers, but there are kind of many boxes that are covered, and this is not 100% correct in that picture. But what you should already see in this picture, and I think that it's accurate, that because if you know that these kind of wiggly lines cannot leave the boxes, and you have one of these kind of, if you have one of these fibers going up where you have lots of yellow boxes, then you will find a fiber, so there's a single fiber where that has large cardinality. So in this picture, I can draw this. Now we have seen that there are many yellow boxes, and suppose I take one of these down here. I know for this kind of box, there are many yellow boxes above that. Then if I take any fiber here, something like this, then because in these yellow boxes, this really has to be a line that never stops and never leaves the interval to the top. This fiber here always has to intersect these lines. And so that then means that this fiber here over this X has to be large because it cannot, and that's a contradiction to our assumption. But I will make this, I will do the counting. So let me do the counting. Okay. So since I plus P is smaller than D, there needs to be there is I0 in N such that the cardinality of J over J larger than 0 such that Ij is in H has to be larger than m to the p. Because if that would be smaller for all of them, that would be smaller for every I, then, but they're at most mi's, so if then that would mean that the cardinality of H would be smaller than m times m plus p, so it would be smaller than m to the 1 plus p. And so this would follows diametrically from here. So if you want to call this here double star, this is really follows immediately from double star by double star. Okay. Yes, thank you. Yeah. And so this I naught, if you want to draw this here, this is the I naught here. And this is then I naught plus 1. And so the only thing now I have to say is that for every x in this interval, the fiber will be large. But this is almost immediately. So now fix this I0, and let take any x in this interval. So this is, of course, this should be divided by m. Okay, and now let J be in N such that I0J is in H. Erase all of this. So this really, if you're allowed me to draw this again, it should be really divided by m. And so you take one of these. So maybe this one here is now you take this one here to be our j plus 1 m. And so I know that this j plus I0j is in H, so it's colored. And so this means there's this wiggly line that doesn't leave the box. And so now I take any x and I just have to show that then this hits the interval. So this really just now is just our definition. So since the j is still there, that's good. Since I0j is in H, this means that fjx is in this interval. By definition of H. I mean, if you can see, that's really the definition of H. If you have anything in that interval, then it has to be, the image has to be in that other interval. And so hence, really, and you want to write this out, let's write it like this. J plus 1 intersects the fiber over X. So that means that for every J in this set, and for every X, the fiber contains something. So that, so thus, hence, cardinality of this fiber is larger than the cardinality of, sorry, let me write this, the cardinality of the set over there. I0j in H, but this cardinality by this equation over there is, what was it, larger than MP. And this contradicts. Okay. So again, maybe, I mean, so this is really, I mean, maybe a good start to recap what we did. And it's really, look, it's the argument is here on this kind of picture. I mean, and what we said was we had this set E, we know that it hits many of these boxes. But each of the fibers and the point of discontinuity of these weakly lines are small. So knowing that the fibers are small is not enough. The point is really the kind of the continuity of this. So we knew that for many of these, you didn't have a point of discontinuity. Okay. But if you would have, so we could all directly reduce to saying that many of the boxes we care about, you know that these kind of weakly lines are continuous, this kind of minimum points. Again, that was not enough. So the argument we had to make was that we also know that most of these boxes, these weakly lines, do not leave the boxes. That was simply because this was continuous, and if they would be continuous, they would have to hit one of these fibers over here. But we know there are just few things in these fibers. So that allowed us to reduce to cases where really, if you look at one of these boxes, you have many of these boxes where there is one of these weakly lines, which is continuous and keeps in this box. And as soon as you know that there are many of those, you have to find a fiber that is large, simply because this makes sure that you cannot have something like in here. I mean, what could you have? You could have something in general that maybe here lies a point, here lies a point, here lies a point, and so on. And so you hit this box, but only in very few fibers. But because you have this kind of function that they go all the way through this box, this cannot happen. You have to have something that lies something like this. And this makes sure that individual fibers cannot pick up, cannot make the dimension of the two-dimensional set large. All right. Okay, I'll just say something about what's following, but this is kind of the last thing about the proof. Any questions?
For any X in...
Yes. Yes. So really, I mean, any X would work. I mean, simply, I mean, that's kind of how it has to be the whole line. Okay, I will so what this gives you here is really a kind of equality of metric dimensions. But of course, as I said this a little bit, I would like to have, let's say, at some point in order to prove Miller's conjecture, do they have this kind of stronger control of the definable sets. So of course, you can see this in the picture that we had there, that we have a little bit more control, right? I mean, it's not completely random, this sets, and which happens to be be nice. Really, we have a lot of this kind of continuity along this picture. So what you would hope to do, and if you think about o-minimality, that's really kind of natural, is you would hope to have some kind of cell decomposition here, right? I mean, so if you look at this picture, it's kind of okay. Can you kind of increase this picture, the niceness of this picture, such that you really would have cell decomposition? So what you would have to do is you would somehow kind of, I mean, first of all, you would have to say what that really means. I mean, it's even if, can you somehow pick one of these, and then above these, it's a nice stack of graphs of continuous functions. Of course, if you're not in the case of o-minimality, there's no hope. I mean, really, the picture I drew here could be in an o-minimal structure, right? Every fiber here is finite that I drew, and that's a bounded thing. That could be very well an o-minimal structure. And so the kind of, you have to say, the first thing is, I want to use my last 10 minutes or so, is to say, okay, what should be cells? What are the kind of objects you're looking for when I talk about this kind of cell decomposition? And I somehow want to propose something, and that I want to use this kind of last 10 minutes or so on doing that. So really what I think if you talk about what's next, so then what's next? And I think I really want to talk about cell decomposition. And so, as I said, what should that mean? I mean, I think really what you're looking for is a kind of a nice notion of stacks, or some kind of notion of decomposition. So really, if you want to draw something in an o-minimal structure, you would maybe, a cell decomposition, you would have something like this, right? That's maybe too symmetric, but it would look something like this. However, of course, in this case, there's no hope that it should be this nice. Really, what you would have to have is lots and lots and lots of functions that look like this in here. So the kind of, you could have something, this line, and this could get closer and closer to these kind of lines. So these kind of, so it's of course hard to write, but you could really have some kind of, as a minimum thing, lines that approach closer and closer to other lines. So there's no, these fibers here, if that is your cell decomposition, and you take a fiber, let's say call this here EX, there's really the best thing you can hope for is that this, I mean, that this E of X, each of these fibers is nowhere dense. So in the o-minimal structure, this would always, you would get to a cell decomposition that these fibers are finite, but here there's no hope. And even so, to tell you how complicated this can be is that, as I said, you could have these kind of limit lines. In an o-minimal structure, you know that each of these lines is uniformly definable. So for each of these things, there's a kind of, you can think I mean, each of these lines here, there's a uniform definition, so that if you vary the parameter, you get the kind of different lines. In general, there's no hope of being able to do this. So what even worse is that maybe in a d-minimal structure, this kind of uniform definability is not true, but at least there you hope that, I mean, locally you would be able to define these kind of functions in a uniform way, not the whole thing. But here in this kind of setting, there's literally no hope to do even that, because we have these kind of limit lines here. I mean, you could have, let's say this EX could be a Cantor set. And in this Cantor set, you have this kind of limit, I mean, this kind of interior points in some sense. And then you would see these kind of lines, and it's very likely that you could not even possibly define a single piece of these kind of limit lines that you get here. So it's really in a setting where you have to prove something, I mean, something more general, or kind of, than you would prove in the cell decomposition, because even this kind of the cells you would have, you have no, if you take one of these kind of limit cells here, have no reason to be definable. So I think the best thing one can do is really, instead of thinking about cells as the individual, as a kind of minimal element, you start thinking of these kind of stacks as a minimal element, rather than start talking about, okay, I have this kind of countable union of cells, or this kind of, you really have to have some kind of control about this whole family. So for example, what you could say, what you could define, it's just more a proposition as, for example, you could say that something like this, you could maybe call a thin stack over some cell down here. Maybe this is a cell C, over some stack C. And this is really, this is a set, maybe you call it X, such that there is, the minimum, so maybe you want to put more restrictions, that there is a nowhere dense set E, and the family CA, A and E of cells, let's say 0 cells, however you want to call them, so graphs of continuous functions, such that, well, X is a union of those. Okay. So that's the minimum you have to add. I think then you also have to add at least that in order to make this picture work, that these lines do not intersect. So you want to have that something like, let me maybe write this easily here, that E of A1 is smaller than C of A2, such that A1 is smaller than E2. But again, in general, as I pointed this out, so maybe everything looks like this, but there's no hope that each of these individual CAs would be definable.
Where does C occur in the definition?
Oh, I should say cells over C. So the projection of CA downstairs is C. So this whole thing here should be C. And so I mean, maybe you even want to write X as something like, maybe this is possible as something like F of E times C. But maybe that's too good to ask for. And then you keep, I mean, again, maybe I say this in a second. And maybe then the next step you do is you have to, okay, well, what should then be?
Family CA with A ranging over E, does not have to be definable.
Yeah, well, I want to prove this for definable sets, but this, of course, makes sense a priori. So, but yes, I mean, you would hope that I mean, you need if you want to prove something like this in an inductive step, you need that X is definable. And so then you would go from, I mean, that's kind of the proposal, the kind of, so now maybe these are the individual objects, and then you would go to, so these are the replacement of cells, and then something I might,
What about E?
Of R, sorry. No, not necessarily definable, right? I mean, even that you do not, I mean, again, each of these fibers here is definable, but the kind of the point is that you will not have some kind of bijection between these fibers that you cannot hope for. That's really too good to be true. Even in the de minimal case, that's too good. So, and then I would call it grid. Okay, you do the same thing for thick stacks, where you replace this kind of the cell here, which is just the image of a continuous function by this kind of bands between continuous functions. And then a grid, again, this is a collection, let's call this C, of pairwise disjoint cells in R to the n minus 1, and the collection, I didn't write very well, but okay. Is given by is given by a collection of pairwise disjoint cells. For each cell, you have this collection PC, and this should be this. I will write this down here in a second. Will be a thin stack, such that the union of the cells downstairs, so they live in R to the n minus 1. This form a grid in R to the n minus 1, and the Z is a union. Z is a union of all the PCs, and of course these PCs, they have to be, okay, that would be now a thin grid of thin stacks. So it's somehow you would have, I mean, if it's hard to draw. I mean, it's kind of the, you have in R3, you would have this kind of thin stack lying like this, and then over each of these cells in the thin stack, there would be another thin stack going up there. Okay, so let me so the grid is somehow well, I mean, somehow I think this might be the kind of the minimal element, because the minimal definable element. So these stacks might be definable. Each of these cells might not. And then this in general, you could hope that then the grids should be definable. Again, the individual cells might not. In this case, even it's not 100% clear that the individual grids are definable, all of the individual, sorry, thin stacks. But because, I mean, think about this, you might have here one of these limit lines you had to cannot define, and then you have this thin stack coming over this limit line coming out of the board, and you don't even know that the limit line itself is definable. So the stack over this limit line will not be definable. So what we really would have to do is we have to get a really good control of the grids, and in particular, really good control of those lines about we can actually talk. So this kind of the lines that are not limit lines. And this is not out of the question. Of course, so this is kind of the most general definition here. So where we would work in this kind of noiseless structures, or where you maybe hope to prove the noiseless structure. You can do this for d-minimal structures. And the same definition here really works. So if you replace this nowhere dense here by okay, you have to be maybe a thin stack, you replace this nowhere dense here by a discrete set. And you make sure that in this kind of definition here that really all these lines are discrete. And then you actually can show the equivalent that d-minimal structures have these every definable set is a finite is a union of finitely many grids. So in a d-minimal structure, we know there's my student Rocco Davino checked this out. I'm not 100% sure. Atipat, Tamo, and Tanyalak, he proved this kind of cell decomposition theorem for d-minimal structures. Correcting something from Chris. I'm not 100% sure whether his proof gives also that for d-minimal structures. That might be the case, but it's a little bit hard to read. So we definitely, something like this works in Tame cases. I also know it works in the locally o-minimal case, and it definitely works in the d-minimal case. The question is whether this can move up to this really kind of general noiseless case. And it's not I made this, we have so much control over this, it doesn't sound as, I'm much more hopeful than I sound like this is, because I try to, let's say what are the complications that arise, but I think most of them you can actually handle. Okay. Yeah, that's it. That's where I wanted to stop. And thank you for coming.